In this video, I want to take our first attempt at trying to solve some of these higher order differential equations. We're going to be using a method called reduction of order in this case. And the idea behind reduction of order is it's going to be a technique that allows us to reduce the order of our differential equation. In this case, we'll be starting with a second order differential equation, which we don't currently have techniques to solve. And by doing some complicated algebra and a bit of few other tricks, we will basically reduce the order from a second order equation down to a first order equation, which we have a whole slew of techniques to solve. So that's going to be our approach. So let's start with the equation that we're going to actually be considering. So let's think about trying to solve the following second order differential equation. It's going to look like a2 of x times y double prime plus a1 of x times y prime plus a0 of x times y equals 0. So we'll start with a homogeneous differential equation here. So this is a linear second order homogeneous differential equation similar to the ones that we looked at in the last video. In general, based on our discussion, again, the long, arduous discussion we had in the last video, I know that the solution to this will take the following form. So this has a solution that looks something like this. Y equals C1 times some Y1 plus C2 times some Y2, where Y1 and Y2 are two separate linearly independent solutions to the original equation. Right? This is one of the things we talked about. The order of your equation will determine basically how many linearly independent solutions we need to create our fundamental set. And so in this case, it's a second order differential equation. We need two linearly independent solutions, y1 and y2, and we take the linear combination of those two functions in order to get the general solution. So in this case, y1 and y2 are linearly independent solutions of the ODE. Okay. So here's where I want to start. Pretty soon, we're going to be solving differential equations where these a's, a1, a2, a0, where these are just constants. But for right now, we've written it in such a way that they can be functions of x. When they're constants, we're going to have a very sort of linear approach to solve these. It's going to make a lot of sense. But when these are functions of x, it's a lot more difficult. And honestly, reduction of order is going to be kind of our only approach. So for now, I want to keep thinking of these a's as functions of x. And I want to think about how we can try to solve this thing. Turns out one of the best ways to solve some of these equations is guessing and checking your way. So solving these is hard. Sometimes basically clever guessing is your best bet. And we'll do an example of this down the line. So what if we can come up with one of these solutions? Let's say hypothetically, if we can find, by whatever means, maybe it is just clever guessing, if we can find y1, is it possible to determine the other, right? Maybe we get, lightning strikes once and we're able to come up with one solution that works. But maybe lightning doesn't strike twice, and we don't know how to find the second solution. Can we use this first solution to determine the second solution? And the answer is yes. That's what this reduction of order is all about. So it's going to require us to know at least one, in this case, or it's going to require us to know exactly one of these two linearly independent solutions in order to find the other one. And we will actually use this technique later. When these are constant coefficients, we'll have one special case where it turns out the techniques that we normally use that normally give us the two solutions we're looking for, where they break down and they only give us one solution. And we're going to actually have to use reduction of order to find the second solution in that case. So that's going to be the big picture. This is going to be a useful method. We're going to have a couple of different places where this gets applied. But the big story is we need one solution, and this method will generate the second solution for us. Okay, so how do we do this? So what is reduction of order? Given one solution, y1 will, if I can write clearly, will be able to reduce the second order ODE to a first order ODE, which we have a ton of techniques for, as I mentioned, in order to find y2. So how is this going to work? Let's think about what we know about y1 and y2. The only thing that we know, so y1 is known, y2 is unknown, we're trying to solve it. And all we know right now is that they must be linearly independent solutions. So let's start with that idea of linear independence. We know that y1, which is known, is linearly independent from y2, which is, as we said, unknown, thing that we're trying to find. What does it mean for them to be linearly independent? Well, we had our definition before that basically says if you take a linear combination of them, so constant times y1 plus a different constant times y2, and set it equal to 0, the only solution is that both constants have to be 0. So basically what it's saying is c1 times y1 plus c2 times y2 equals 0 implies that both c1 and c2 are 0. That's the only way to solve it. But I think an easier way to think about it, especially in the case where we've only got these two functions of concern, is that if that were not the case, if we could find a way to combine some constant times y1 plus some other constant times y2, essentially what we're saying is we would be able to find a way to cancel these two pieces out. We could write this term as the negative of this term. And so we can actually do that algebraically. What we're saying is c1 y1 must be equal to c2 y2 with a negative sign in front of it. And that tells me that y1 would be negative c2 over c1 times y2. So if there's another solution, so let me write that here. If not, so if there's some other solution where there's a c1 and a c2 that work, we should be able to rearrange things and write things out like this. And I'm only allowed to do this if, again, c1 is not 0, because we're dividing by c1 right here. So the only other solution right, meaning assuming the c's are non-zero, is that y1 is a multiple of y2, basically. Or that you could come up with a constant of proportionality. Maybe that's a better word. Instead of a multiple, let me write it this way, is proportional to to y2. They're really the same function potentially with just, again, different constants in front of them. So if y1 was x and y2 was 2x, those aren't linearly independent because I could just basically double the first one and then subtract the second one and you would get 0. So if the c's are non-zero, it would mean that one is a multiple of the other. So the reverse of this, saying that they are linearly independent, means that this is not possible. We can't wind up with this situation, right? So if they're not linearly independent, let me put that over here. If not linearly independent, this is what it leads to, that one is a multiple of the other. So because R's are linearly independent, it means that that can't be the case. So because they're linearly independent, y1 and y2 are not multiples of one another. And what this means is, if I look at the ratio of the two functions, so if we consider y1 over y2, in fact, let's do it the other way, y2 over y1, what I'm assured of is that this has to be some function of x, not a constant. Right, we could basically come back up over to this equation and do the same thing. Instead of dividing out by the c's, I could just divide both sides by both the y1 and divide both sides by this negative c2. And we'd get that. So basically at this step, you could divide both sides by y2. And we get y1 over y2 is some constant because it would just be a ratio of these two other constants. But that's under the assumption that they're not linearly independent. If they are linearly independent, then the only solution here is 0. It means one function is not proportional to the other. One is not a multiple of the other. If one function is not a multiple of the other, then when I take their ratio, I'm guaranteed to get some function that depends on x. I'm not getting a constant if these things are linearly independent. Okay, so because they're linearly independent, y1 and y2 are not multiples of one another. And so when we take their ratio, we're going to get some function that's not a constant. That is our starting point. And with this, we can come up with a clever way to write y2 in terms of y1. It's going to look like u of x times our y1 of x. So y2 is some function of x times y1. It can't be a constant times y1. It has to be a totally different function of x times y1. Okay, so this is what we're presuming our second solution looks like. So we know our second solution takes this form. So it should satisfy the original ODE that we started with. So basically what I'm claiming is this y2 also needs to be a solution to this equation. That's the whole point. We're trying to find a second solution that satisfies the equation, and we have assumed so far that it has to take this particular form. What that means is I should be able to plug this y2 into this differential equation and have this equation be satisfied. So let's do that. But before we do that, I want to clean a few things up. Okay, so first of all, I'm going to stop writing all these dependencies on x because we're going to have all these terms showing up everywhere. We just need to keep in mind u depends on x and y1 depends on x, and also y2. y2 depends on x. These are all functions of x, and I can stop writing these parentheses or stuff just gets very long. The second thing is the ODE that we want to solve is the one that I wrote up there, but to make things a little bit more clean, I would prefer if this leading coefficient were a 1. And right now it's not a 1, right? Arbitrarily, it can be any a2 of x, some function of x. But what I'm going to do is basically take this equation and divide out by a2 of x every single term so that I can make the leading coefficient 1. We did something very similar back when we were doing integrating factor for linear equations that were first order equations. So I'm going to divide the ODE by a2 of x to make the leading coefficient 1. And it'll just make our algebra a lot easier to follow. I can do that, right? The only restriction would be, well, you can't divide by this if it's equal to 0, but by definition, for this to be a second order differential equation, we already have the restriction that this coefficient can't be 0. At least on the interval that we're interested in solving this differential equation on, the leading coefficient cannot be 0, so we are allowed to divide by it. So keep that in mind. So I'm going to rewrite the a2 of x times y double prime plus a1 of x times y prime, times y prime plus a0 of x times y equals 0. I'm going to rewrite this as the following. It becomes just y double prime plus some function that I'm going to call p of x times y prime plus some other function I'm going to call q of x times y equals 0, where that p of x is just this coefficient divided by the a2 that we already divided through by. So p of x is just a1 of x over a2 of x, and similarly the q of x term, that coefficient over here, this function is just a0 divided by a2. So this one's going to be a0 of x divided by a2 of x. So this is going to be a much easier equation to deal with. So basically get your second order differential equation into this form by dividing by the leading coefficient if necessary. And this is the equation that we're going to be solving. So now plug in our expression for y2. So you'll recall y2 was equal to u times y1. And again, I'm going to start dropping the x dependencies. So I'm just copying it from this line. y2 was u times y1. That's going to be fine when we plug it in right here, but for this term and this term, I'm going to need to plug in the derivative and the second derivative. So I need y2 prime and I need y2 double prime. So let's find out what those look like. What is y2 prime? Well, if I remember that both u and y are functions of x, when I take the derivative of this product, I'm going to have to use product rule. So let's do product rule on this. The product rule says I will get the first times the derivative of the second plus the second times the derivative of the first. So here's the first times the derivative of the second. Here is the second times the derivative of the first. So make that clear, that's a prime. So there's what the first derivative looks like. What about the second derivative? For the second derivative, I need to take the derivative of the first derivative. And each of these, again, is a function of x, so I'm going to have two other products that I'm taking a derivative of, and I'm going to need to use product rule on each of these two pieces. So let's start with this one. When I take the derivative of this, I'm going to again get first times the derivative of the second, but the derivative of y1 prime is going to be y1 double prime. So here's first times the derivative of the second, plus second times the derivative of the first. So here's the second, and the derivative of the first will be u prime. So here, this is just the derivative of this term. Now let's do the same thing for this term. We'll have, again, first times the derivative of the second, plus second times the derivative of the first. And we get that. And I can clean up this by noticing that this term here matches this term here exactly. So by combining those like terms, we can rewrite this as u times y1 double prime plus two of these u prime y1 prime terms plus u double prime y1. Okay, so here are the expressions for y2, y2 prime, and y2 double prime that we're going to be plugging into this equation. So sub into the ODE. And we'll see what we get. We'll go from there. But the idea is, again, y2 is supposed to be a solution to this, so let's plug it in and see what things start to look like. So the first thing is I have y double prime, so that means it's going to be this whole term. Then I'm going to have p of x times y prime, so p of x times this whole term. And lastly, I'll have q of x times y, so q of x times this whole term. Add them all up, and it should be equal to 0. Okay, so let's do that. My first term is just that second derivative piece, so it's going to be u times y1 double prime plus 2u prime y1 prime plus u double prime y1. So there's the second derivative term. See if I can get this all on the screen at once. So far I've just taken care of this piece, the second derivative term. Now let's do this piece. So the next term is going to be plus p of x times y prime. So again, I'm going to drop the dependence on x. We'll just know that p is a function of x. So it's going to be p times, here's our expression for y prime. So u y1 prime plus u prime y1. And lastly, we need q times y. So q times, here's our expression for y2. That whole thing has to be equal to 0. Okay, so here is all the terms that we found plugged into the differential equation. And it looks scary, but I want to try to clean some things up. And I'm going to do it by just algebraically reorganizing and regrouping some of these terms. So the first thing I want to do is basically kind of cleverly pick out some of these terms that involve y1 double prime, y1 prime, and y1. So I'm going to group this term here, and this term here together. And we'll see why in just a minute. So again, I don't expect you to have intuition for doing this, but hopefully it will be semi-obvious once we see it. So basically, let me just change the color here. We've taken care of this one, and this one so far. So let's write the rest. What else is left? I'm going to have, let's see, which ones can I group together? Well, this one right here involves y1. This also involves y1, so maybe I could group those two together because I could factor a y1 out. So let me group this one and this one together, and this one will just keep kind of on its own. So we'll have 2u prime y1 prime plus we've got u double prime y1 plus p u prime y1 equals 0. So all I've done is reordered these terms. These ones are going to be grouped together, and these ones are going to be grouped together. These ones I'm grouping together because I can factor a y1 out. These I'm grouping together because I'm going to be able to factor a u out, and then another important reason. So let me just factor that u out, and maybe it'll be a little bit more clear once we factor that u out, what we're dealing with over here. So there's that piece. Let's do the same thing over here, so I'm not touching this one. But this last one, let's factor the y1 out. So this one will be u double prime plus p u prime times y1. Good enough for now. And actually, if I'm clever, well, yeah, that's fine. We can do it like this for now. I actually want to group these in a little bit different way. Let me undo this. Instead of grouping these together, so all I'm going to do is erase these. Sorry. I think I have a better grouping. Okay, so let's come back to this stage. I've grouped these three together, and I have the remaining pieces here. So instead of factoring out, because in this one I factored out a u, let's factor out a u prime, because over here we've got basically this term involves a u prime, and this term involves a u prime, let's group those two together, and let's have this one be the odd man out. I'd rather factor out u's if possible. So I'm going to have basically a 2u prime y1 prime plus a pu prime y1. So that is this term and this term. I'll group those together. And then we'll have this one be the odd man out, plus u double prime y1. And so let's factor the u prime out of this one instead. It'll be a little bit nicer to deal with. So u prime gets factored out, and we're left with 2y1 prime plus py1. Good. And then this last term will just be u double prime y1. Don't forget my plus sign there. Okay. So again, I've just rewritten this line by grouping. This piece I'm not going to touch for now, but this piece we can actually simplify. We've got to remember what we're dealing with here. I notice that this looks awfully familiar. If I compare what I have written right here to the left-hand side of our differential equation that we're trying to solve to begin with, they look the same, right? It's y double prime plus py prime plus q times y. Well, here's y double prime plus py prime plus q times y. And we already know that y1 is a solution of this differential equation and therefore a solution of this differential equation, meaning when I plug in y1 to this differential equation, it is satisfied, it is true. So when I plug in y1 for here, y1 double prime, y1 prime here, and y1 here, what does this have to be equal to? It has to be equal to 0. So this entire term is 0 because y1 is a solution to the ODE that we were trying to solve. So that whole term is going to disappear, and now I'm going to be left with these two pieces. Which is kind of nice. I'm going to, again, just write them in a slightly different order. So I'm going to write this as u double prime times y1 plus u prime times 2y1 prime plus py1 equals 0. Okay, so again, this looks kind of scary. It's still a second order differential equation, but it's not as bad as it looks. First thing, we already know y1. y1 is the solution that you'll recall is somewhere up here. Known. y1 is known. We know y1. And that means if we know the equation y1, we also know what y1 prime looks like. We can just take the derivative of that known equation to get another known equation. So I know what this looks like. It's just some function of x. This is just some function of x. And this whole thing over here is just some function of x. So these are all pieces that are known. It's really only u that is unknown here. So recall that y1 is known. So only u is unknown. And we have a second order differential equation for u. But notice that it is also missing the third term. Normally we have u double prime plus u prime plus u would be the form of our second order differential equation. It might not seem significant, but this is actually a big deal. I can rewrite this equation in terms of a new variable to convert it into a first order differential equation. If we let some new variable, let's call it w, be equal to u prime, then what happens when I take the derivative of that? So what is w prime? Well, w prime is now u double prime. And so what looks like in terms of u a first derivative and a second derivative, in terms of w are just a first derivative and no derivative. And I can rewrite this equation in terms of this w, and it'll become a first order differential equation. We'll get out of this u double prime, which just becomes w prime times our y1, plus u prime, which is just w, times 2y1 prime plus py1 equals 0. So this is a first order ODE for W. So if we can solve for W, once we know W, we'll come back here, use our known value of W to solve for U. Once we know U, we can, and our known value of Y1, we can go back and solve for Y2. We can find our other solution. So that is going to be the remainder of what we need to do. We need to solve this for W. And it turns out to be a first order ODE. It also is linear, right? There's no weird nonlinear dependence for the W, so we could solve this using integrating factor. We could solve it. It turns out this is also separable. So we have a couple of approaches. This is linear, meaning we could use integrating factor. And it also is separable. So we get to pick. Pick your poison. I'm going to treat it like a separable equation. So let's treat it like it's separable. I'm going to rewrite the equation. So it's dw dx, that's what this w prime is. It's a derivative with respect to x, times y1 plus w times 2y1 prime plus py1 equals 0. Why don't I need to rewrite this y1 prime as like dy1 dx? Well, I could, but it's not important because, again, y1 isn't an unknown. We know what y1 looks like. We know what y1 prime looks like. The second we know what y1 is, we can take its derivative to get y1 prime. So I'm not going to bother with that. I just need to separate all the w's onto one side of the equation and everything else, because all these other things are simply functions of x. y1 prime is a function of x, y1 is a function of x, and x itself, our dx, is a function of x. So we can kind of do this cleverly. We don't have to necessarily even move them to different sides of the equation if we don't want. What's going to be the easiest way to do this? Yeah, well, let's just do it. It'll be easier. So what I'm going to do is, let's do this one step at a time. First thing, let's multiply everything by dx. So I'm going to get dw times y1 plus w times 2y1 prime plus py1 dx equals 0. And I'm going to move this whole piece over to the other side of the equal sign. So we'll have dw times y1 equals negative w 2y1 prime plus py1 dx. So I've just moved this term over to the other side. I'm going to now divide by the w to get it onto this side, and I'm going to also divide by y1 to move that to the other side. So I'm going to have dw over w on the left, and on the other side I'm going to have this negative 2y1 prime plus py1 dx over y1. So I've now separated all these things that are a function of x over to this side. Everything that involves w is over here on the left-hand side. And now we can integrate both sides. On the left, I'm going to get the natural log of the absolute value of w. And on the right, I'm going to split this up into a couple of separate integrals. So the first integral I'm going to look at is, let's factor that 2 out, and I'll have negative 2 of y1 prime over y1 dx. So that's these two terms are accounted for with this part. And then I'm going to do these parts separately. So for the second part, I'll have minus the integral, again, because this minus distributes through. We've got our p, and the y1 over y1 is going to cancel. So I'm just going to have the p times dx here. Where do we go from here? So again, let's leave the left-hand side alone. What does this side look like? Well, y1 prime over y1, this takes the form of the natural log of y1. So you could do essentially a U-substitution if you wanted to here. Think of this sort of as your du over your u, but it's basically anytime you see a derivative over the original function, that should tell you you're dealing with natural log. So I've got a negative 2 natural log of the absolute value of y1. If you want to take a minute and do this with the U-substitution, by all means, go ahead and do that. And this last piece It's just the integral of p dx. We don't know exactly what p is. I mean, it's given, but we don't know it specifically for this problem, so we can't actually do this integral until we have the function p of x. So we'll just leave it as the integral of p of x dx. So our goal is to solve for w. Again, once we have w, we can then try to solve for u. Once we have u, we can solve for y2. So we've got to go a couple steps up. So let's solve for w. First thing I'm going to do is get rid of this natural log. So let's exponentiate both sides. And I should make it clear there was essentially plus some constant. Let's call it plus some c1. I forgot to make it explicit, right? When we integrated this, we always wind up with some constant of integration. So when I exponentiate both sides, I'm going to have absolute value of w, and on this side I have e to that whole mess, but that's the same as e to the -2 natural log of the absolute value of y1 times e to the negative integral of p dx times e to the c1. We can wrap basically the absolute values that showed up here kind of into this e to the c1, right? These are all, because they're all exponentials, they're all guaranteed to be positive. We can drop our absolute values. I can clean this up. We can use log rules to move this -2 up into the power of this thing. So basically what we've got is, let's write it this way, natural log of absolute value of y1 to the -2. Again, we've got this e to the negative integral of p dx, and this e to the c1. So let's just say this is some new constant. It's a constant that allows us to drop the absolute values here, because again, these are all exponentials. E to anything is still going to be positive, whether the power is positive or negative, so we don't need to worry about those absolute values. So what we have is w is equal to some new constant, we'll call it c2. E to this natural log, they cancel. I'm just going to have basically absolute value of y1 to the -2 power. And then we've got e to the negative integral of p dx. If you think about this, this is the same as basically rewriting it as w equals c2 times e to the negative integral of p dx. And we really just have a y1 squared in the denominator. And I can drop the absolute values here, right? The negative sign is what makes it show up in the denominator. But I can also drop the absolute values because we're squaring it regardless. So we don't need the absolute value if we're squaring it. And we have now an expression for what w looks like. Here is an expression for w. So this is not our answer, but it is our answer for what w looks like. Now find u. But what was our relationship between u and w? We got to come back up here. Here's our relationship between w and u. So recall that w is equal to u prime. So what does that mean the relationship is if I want to solve for u? So basically, you could think of this as w equals du dx. How do I solve for u? Well, we're going to need to integrate both sides. So if I do the integral of w dx, I should get the integral of du dx dx, which cancels and just gives me the value of u that we're looking for. But again, because we're integrating here, we will also wind up with some new constant of integration. We'll call it C3, because I'm, I think, to my third constant. Yeah, we've used up C2. So this is the idea. The next thing I need to do is integrate w, integrate this whole thing with respect to x, and then add some new constant. So u is equal to the integral of w, which is C2, e to the negative integral of p dx over y1 squared. Integrate that whole thing with respect to x, and then add some new constant C3. And technically, I should have made, make it clear. Let's say the C3 was already going to be on the left-hand side instead of the right-hand side anyways, just to make life a little easier. Okay, so there is now my expression for what u looks like. We have some choices here. we can actually, because we haven't specified, and this needs to be true for all values of the constant, the relationship, we can actually pick ones that are convenient to kind of clean things up. So let's pick some values that make this nicer. I'm going to pick C3 equals 0 and C2 to be equal to 1 for our value of u. And again, we're going to be allowed to do this because ultimately, we're not trying to find u, we're ultimately trying to find y2, which is just going to be u times y1. And then we're going to take a linear combination, coming way back up here, of y1 and y2. So there's already going to be some other constant in front of it. So I can not worry about these constants. We're going to have another constant later. So let's pick some convenient ones for the time being to get that u is equal to the integral of e to the negative integral of p dx over y1 squared dx. And again, this is now 0. This was 1. So what is y2 then? y2 of x, the thing that we actually wanted, is just going to be this u times the original y1. Again, let's just go back and remind you one more time. Where am I getting this from? Right here. y2 is supposed to be equal to u times y1. Well, we just found u. y1 is some known function that we've supposedly known from the beginning. So it's going to be simply y1 of x times this integral. This is our expression for our second solution. Whew. Okay, so that was a lot of work. Obviously, kind of a non-ideal way to do this. But let's see this in practice. Let's do a problem, and we can actually kind of go through it a couple of different ways. We can go through basically the whole process, and then we could also go through one where maybe we just plug directly into this formula. So let's see both. Let's do a couple of examples. So let's do for this first example, let's start with a relatively easy one here. So consider, let's do y double prime minus 4y equals 0. And so this is valid on all reals from negative infinity up to infinity, right? We're good to go here. First, let's verify that y equals e to the 2x is a solution. Okay, so I'm giving you one solution. This is going to be the one that we call y1. So let's call it y1 while I'm at it. So y1 equals e to the 2x is a solution. Well, let's check. What is y1 prime going to be? Well, what's the derivative of e to the 2x? We would get 2e to the 2x by chain rule, right? E to the 2x times the derivative of the stuff up here would give us the extra factor of 2. Take the derivative of that, and we will wind up with 4e to the 2x. And so when we plug these in, we'll get y1 double prime for our first term. So we'll get 4e to the 2x minus 4 times the original value of y, which was simply e to the 2x. And what does that equal? Well, I've got 4e to the 2x minus 4e to the 2x. We do indeed get 0. So we get something that does indeed work. 0 equals 0, basically. We've plugged it in. It satisfied the original condition. So let's try to find the second solution. So find another solution. y2. And so what we'll do is we'll start off saying, okay, well, y2 is going to be some u times the original y1. And so for us, that means it's going to be some u times e to the 2x, because e to the 2x is our original y1 value. what will y2 prime look like? Well, the assumption again is that u is a function of x, so I can't just treat it as a constant. I have to do product rule here. So what is the derivative of this product? I'll get the first times the derivative of the second plus the second times the derivative of the first. So here's what that looks like. We've got the first times the derivative of the second, and here's the second times the derivative of the first. Then do the same thing to get the second derivative. We'll do some more product rules, so I'll do first times the derivative of the second plus the second times the derivative of the first, which will be, again, we'll get a u prime times 2e to the 2x. And that's just this part. Now we need to do product rule on this part. So I'll get first times the derivative of the second plus the second times the derivative of the first. And as before, we'll be able to combine those two terms together and rewrite this as u times, in fact, let's pull the 4's out if we want, because it doesn't really matter. 4e to the 2x. This one is going to be u prime times 4e to the 2x because I've combined this 2 and this 2 into 4 plus u double prime e to the 2x. Okay, and now all we do is sub these in. Notice our equation was nice because the leading coefficient was already a 1, so we didn't have to do anything like dividing out, but just keep in mind, if this function in front of the second order derivative isn't a 1, you will have to divide through on the whole equation by that, but we're good, we don't need to do that here. So we sub that into the ODE. So again, I'm just plugging these values that we found back into this ODE. So it's y double prime minus 4 of the original y. So I need y double prime, which is this, minus 4 of the original one here. So for us, we're going to get u times 4e to the 2x plus u prime times 4e to the 2x plus u double prime times e to the 2x minus 4. Right, so this is just the y double prime term, minus 4 of the original y, which is u e to the 2x. That's supposed to be equal to 0. And sure enough, we can kind of go through and check and see how things are going to work. And notice that this term here winds up canceling with this term here. Here I have 4e to the 2x times u. Here I have 4e to the 2x times u, but with a negative sign. So this whole piece will cancel with this whole piece. And this is always what we're hoping to have happen. The goal should always be to get the u term to cancel out and leaving us with only u double prime and u prime. We have, at this point, and we can factor the e to the 2x out if we want, it doesn't really matter. We have e to the 2x times, in this case, u double prime plus 4u prime equals 0. So all I've done is basically take these two terms, factor the e to the 2x out, and just reorder them. So here's our differential equation. I can cancel the e to the 2x if we want, because I can divide through by it. It's always going to be some positive non-zero number. And when I divide through by it, on the right-hand side, 0 divided by this non-zero number is just going to be 0. So we can divide by, well, however you want to think about it. Divided by e to the 2x, or multiply by e to the negative 2x, however you want to think about it. Here's our differential equation for u. It is a second order differential equation. We need to let w equal u prime, which implies that w prime will be u double prime. And now this equation becomes w prime plus 4w equals 0. This is a straightforward equation. Again, this one is Typically, it's going to be linear, so you'll always be able to use integrating factor. Very often it will be, if not always, it will be separable. So you can kind of take your pick. We did separable last time. Let's do integrating factor on this. So linear, use integrating factor. So my integrating factor, mu of x, is going to be e to the integral of whatever the coefficient is sitting here, dx. So it's going to be e to the 4x. And that tells me that we've got, we'll have d dx times e to the 4x times w on the left-hand side, and on the right-hand side, we still just have 0, because even when we multiply it by e to the 4x, we still have 0. So let's just check and make sure I didn't screw anything up. When we take the derivative of this product, you'll get first times the derivative of the second, so I'd have e to the 4x times w prime, plus the second times the derivative of the first. So I'd have a w times the derivative of this will be 4e to the 4x, and that would pick up the extra factor of 4 that I would have here. We'd have just this with the e to the 4x out in front of it. So we're good. So let's integrate both sides with respect to x. We will get e to the 4x times w equals some constant, and therefore w equals ce to the negative 4x. But again, that's just what w is. If this is what w is, what is u? Well, u needs to be, according to our relationship right here, right? The derivative of u is w, so to find u itself, I need to integrate both sides of this. So we need to integrate our w in order to get u. So it's the integral of ce to the negative 4x dx. Let's call this, while we're at it, let's just call it c1, because we're going to introduce some more constants in a minute anyways. What is the integral of e to the negative 4x? Well, that's going to give us, in this case, we will get, again, e to the negative 4x, because the integral of the exponential is an exponential of the same form. Let's just make sure I get the coefficient in front correct. I have the c1 that's being carried over, and I will be dividing by the negative 4 that will cancel out when we were to take the derivative, plus some new constant, c2. So at this point, we can now say that y2, the solution we're looking for, is again just u times y1. And u times y1, well, here's my expression for u. The expression for y1 was somewhere way back up here. Here we go, e to the 2x. So this is going to be u times e to the 2x, but we already found our value of u. Remember, we get to pick the c1 and c2 that make this convenient. We don't want to totally wipe everything out, so we've got to be a little bit clever about how we're going to pick these things. But let's just say, in fact, let's just do it. Let's hypothetically say, let's let C1 and C2 just stay that way for now and just see what happens if we were to pick them out later, just so you don't have any doubt that what we're doing is okay by picking specific values. So what would I get out of all of this using the generic version of u that still has the constants? I would get, when I multiplied e to the 2x by this first term, e to the 2x times e to the negative 4x, I would be left with my negative c1 over 4 e to the negative 2x is what I'd be left with there. And then for the other term, I'd have c2 e to the positive 2x. Okay, so here's what we've got. This piece here is already of a form that matches y1. Right? So this piece of it isn't linearly independent. We don't need it. So I can ignore this whole piece because it already takes the form of y1. So might as well let c2 be 0. So let c2 be equal to 0 because that already takes the form of y1. That'll kill off that term. And over here, might as well let c1 be equal to, I don't know, negative 4. So that we get some nice cancellation here and just wind up with y2 equals e to the negative 2x. And I'm allowed to do that again because what I'm calling C1 and C2 down here are different than the C1 and C2 when we try to construct our general solution, right? We have one solution here. Here's a second linearly independent solution. The general solution to the original ODE we'll use new letters instead of C1 and C2, is going to be basically, remember y equals we'll call it 3 times y1 plus C4, just so I'm not recycling letters, times y2. And so for us, that's going to be C3 times y1, which was e to the positive 2x, plus some new constant C4 times e to the negative 2x. So this is the general solution to this differential equation up here. Given that we knew one, we were able to easily find the other. So in the next video, we'll have a much easier way to solve this differential equation, not having to have one of the solutions known and using that to find the other. But this technique will be very, very useful going forward. So let's try it on one more equation. In general, I think it's much easier to just go through the process that we went through instead of using this formula. I suck at memorizing formulas, so but technically you could also basically just plug into this formula to get the answer that we're looking for. So maybe we can try one where we just plug into the formula and kind of see how that goes as well. But in general, I would strongly recommend this process. And in fact, on the exam that we eventually have that covers this, I may very well ask you to explicitly go through the process as opposed to just having that formula memorized. So let's try another one. But let's just hypothetically say we're okay with plugging into the formula, which again on the homework and things like that is totally fine. So let's do this one. X squared y double prime plus 2x y prime minus 6y equals 0. And I'll tell you what y1 is, but I want to just think about it first because we can probably have us get a good guess for what y1 should be just based on looking at this. If I look at the coefficients here, the leading coefficient of the y double prime term is an x squared. The coefficient of the middle term, which is y prime, involves x, so 2x, and the last one is just a constant. And when I add them all up, I get 0. What that tells me is that if I'm adding up all these pieces and getting 0, they all have to cancel each other out in some way in order for us to get 0. And for them to cancel each other out, they must all look more or less the same. So here is one trick that we can think of. If I want this term to look the same as this term, and I want this term to look the same as this term, it starts to give me a relationship between what y and y prime and y double prime are. It looks like they're going to all involve some polynomial form, right? If this term has an x squared in it over here, I need this one to also involve an x squared. Where can I put that x squared? Well, it's not sitting out in front anywhere, so the only place the x squared could go would be somewhere involved within the y itself. So what if we just did y equals x squared? Well, if y is equal to x squared, this would be 6x squared, right? What is the derivative of x squared? Well, it would be a 2x, and the 2x would go along with this 2x to make this term also involve x squareds, right? This would wind up being, 4x squareds. And then similarly over here, this x squared second derivative would just be the number 2, and it would go with this x squared to also be an x squared, and they would all now look like x squareds. And it turns out that's kind of one way you can work your way, guess and check your way to the answer that, in fact, in this case, y1 is x squared. So we can verify that, again, just if you want to check, right, if y1 equals x squared, y1 prime is 2x, y1 double prime is just 2, and we would plug them into the differential equation to get y double prime, which is 2 times x squared, plus we'd have y prime, which is 2x, just do it all in parentheses, 2x times the 2x that's already sitting there, so times 2x, plus, or in this case, minus 6 times y, which itself was x squared. And we can see I'm going to have 2x squared plus 4x squared, which is 6x squared, minus this 6x squared, which is indeed 0. So that's one intuitive way you can kind of try to guess and check your way to some of the answers on some of these, is by looking for, in this case, having this clue that, hey, this y must wind up being a polynomial in order for us to get kind of the cancellation that's required to make all these terms look similar. Okay, so we found our one term. Find the second solution, y2. So we can go up to our formula, which I will just write down for us. y2 is equal to y1 times the integral of e to the negative integral of p dx over y1 squared dx. And all we need to do is make sure that the equation is in the right form. Remember, the equation had to be in the form with ODE is basically y double prime plus py prime plus qy equals 0. Oops, I missed a prime there. There we go, prime. So I need the leading coefficient to be 1. It is not currently 1. So how do I get the leading coefficient to be 1? I need to divide the whole equation by x squared. Our ODE is going to be, get this all on the screen at once here, dividing by x squared, we will get y double prime plus 2x over x squared times y prime minus 6 over x squared times y equals 0. Right? All we had to do was divide by x squared to get this. Keep in mind that this does lead to a restriction in the domain. It's true of the original equation. This isn't a second order differential equation when x is equal to 0, because when x is equal to 0, this term gets killed off, this term gets killed off, and we just have this, negative 6y equals 0. So x equals 0 is off limits anyways, which makes it okay to divide by here. This is only going to be valid on an interval that doesn't include x equals 0. So basically, we could stick to all the positive numbers or maybe stick to only negative numbers in our domain, but x cannot be 0. So put that also in parentheses. Note that x cannot be 0, but that was true of the original differential equation anyways. It's going to be, in that case, not even a differential equation when x is equal to 0. We can just solve an algebraic equation to find the solution at that point. Okay, so here is our differential equation, and that means this term here plays the role of what we were calling p, and this here plays the role of what we were calling q. And so I can simplify this, cancel 1x with one of the x's here, and this is just 2 over x. So our p of x is simply 2 over x. And again, what was our y1 was equal to x squared. So we can plug those into the formula here to get the solution if we want. So y2 is going to be y1, which is x squared, times the integral of e to the negative integral of p of x, which was 2 over x dx. And then the whole thing is over y1 squared, or again, y1 was x squared, so that means this is going to be over x to the 4th, x squared quantity squared. So here is our expression. We can go through this and start to kind of clean some stuff up. So let's start with that inner integral. For now, let's just stick with this. But what is this integral up here going to be? So what's the integral of 2 over x? Well, that's just going to be natural log of x. So we've got e to the negative 2 natural log of the absolute value of x. Still have this outer integral that we haven't touched yet. So what is e to the negative 2 ln x? We can rewrite that. So again, I've got my x squared out in front. I'm not touching this outer integral yet. We're just touching this, cleaning up this inner one. So this is going to be e to the natural log of the absolute value of x raised to the negative 2 power, right? My log rules, this thing out in front of the log can come up and become the power of the argument. We've got e to the natural log. That's going to cancel. So I've got my x squared times the integral of, now I just have basically absolute value of x to the negative 2 over x to the 4th dx. But what is the absolute value of x raised to the negative 2? That's the same as 1 over the absolute value of x squared. If we're squaring it, we don't need the absolute values anyways. So this whole thing is going to be x squared times the integral of, we can call this 1 over absolute value of x squared. We also have the x to the 4th that's already sitting down here, dx. Again, I can drop the absolute values because we're squaring it anyway, so it's just x squared times x to the 4th, which is going to be x to the 6th in the denominator. And we've got dx over x to the 6th. So this whole thing can be just written as x squared times the integral, basically x to the negative 6 dx, if you want to think of it like that. What is the integral of x to the negative 6th? Well, we can just do power rule on that. So I'll have x squared times, the integral of x to the negative 6 is going to be 1 power higher, so it's going to be x to the negative 5th, and I need a negative 1/5 in front of that to cancel that out. Again, plus some constant that we'll get. And when I distribute through the x squared, we're going to get negative 1/5 x to the negative 3 plus c x squared. This part can be 0 if we let c be equal to 0, because this part, again, matches the original y1 that we were given, right? One of our solutions was already x squared. We don't need the part of y2 that matches y1, so we can let this part off entirely. Here is a second solution that will work, basically x to the negative 3rd power, because we're going to be able to use other constants in front of all of this. So this basically is our solution. y2 equals negative 1/5 x to the negative 3. And ultimately, we can even, when we construct our general solution, we'll see that we can even do some stuff with this negative 1/5. The general solution to the ODE is going to be that y is equal to some constant, we'll call it c1, times the original y1, which was x squared, plus some c2 times negative 1/5 x to the negative 3rd power. And we can see who needs this negative 1/5 anyways if we've got this c2 sitting here. So we could really just, if we wanted to, call this c1x squared plus some other constant, c3 x to the negative 3. So that will totally work as well. And so there's what our general solution to the original differential equation, sitting way back up here, would look like. Okay, so this is the approach. Again, there's two methods. There's the plugging directly into the formula method, which, as you can see here, is still kind of can be potentially a lot of work. And then there's the one where we actually follow the process. And I really would prefer that you at least go through the process a couple of times, as opposed to strictly always just plugging into the formula. So do get a little bit of practice of both. But this is one method that we will use going forward to help us solve some higher order differential equations.